Hello students, in this video we'll discuss how to find the curvature of a graph of a function. If we're given a function y equals f of x, where x is between a and b, this gives us a function. There's the x-axis, there's the y-axis, and here's a and here's b. We might get some function that looks like this. And we're interested in the function between the points a and b, so in particular we're interested in this portion of the function. And that portion of the function defines a curve. So this will define a curve. And we can write down what the curve is, gamma of t is equal to t I hat plus f of t j hat for t between a and b. Now, we know that s, the arc length parameter, will be the integral from, let's say, a up to t of the length of this curve. So what will the length of this curve be? So if I do gamma prime of u, it'll be I hat plus f prime of u j hat. And so this will be the square root of 1 plus f prime of u quantity squared du. Now in principle, we need to know what the function f is to find the arc length parameter. There's no way to write down a simpler formula for the arc length parameter than this. So if I'm interested in finding the curvature, we have to use the general parameter formula for curvature. So let's recall that the curvature is the length of the curvature vector, which is the length of dt hat ds, where t hat is the unit tangent vector. That's the formula for curvature. Now, what we have is this. So we can note that t hat, of course, is d gamma ds, but d gamma ds is really d gamma dt times dt ds. That is the chain rule. And so now we know that ds dt is just going to be this expression over here, 1, the square root of 1 plus f prime of t quantity squared. And so now we know what the reciprocal of that will be. So in other words, what we have here is we have that the derivative of this curve, so this tells us that if I do one more derivative, the derivative of t with respect to s will be the derivative with respect to s of d gamma dt times dt ds plus d gamma dt times the second derivative of dt with respect to s. And so this tells us that I get a nice formula for the curvature. So the curvature is going to be the length of this vector. So the curvature is going to be the length of this vector over here. And now let's simplify this over here. So what's d by ds? D by ds is d by dt times dt ds. So this will be the length of d gamma squared dt squared times dt ds quantity squared plus d gamma dt times d squared t ds squared. So that will give us a curvature, and it turns out that this will simplify. This simplifies to curvature is equal to the length of gamma prime of t cross gamma double prime of t over gamma prime of t quantity cubed. If you run through this calculation, you'll get this expression for curvature in general parameters. So this expression is much more complicated, but it turns out for this particular problem, it will help us in a nice way. So we already have gamma prime of t over here, so our gamma prime of t is just going to be I hat plus f prime of t j hat. Gamma double prime of t is even simpler. It's just f double prime of t j hat. Because the derivative of I hat, there's nothing there. It's constant. It'll be 0. So if we want to cross gamma prime and gamma, what will we get? So if I do gamma prime cross gamma double prime. What that is that's going to be I hat plus f prime of t j hat. And I'm going to cross this with f double prime of t j hat. Now I hat cross j hat is k hat, so this is going to be f double prime of t k hat. And j hat cross j hat is 0, so this whole top expression over here is just f double prime t k hat. So the curvature for our formula will simplify to f double prime of t in the absolute value divided by the length of this expression over here will be this term over here. So this is my arc length parameter. I'm going to raise this thing to the third power. So I will have a 1 plus f prime of t squared raised to the 3/2 power. And this gives me the formula for the curvature of a function at a point t in the interval a to b. Now, we can notice that the curvature is equal to 0 if and only if the second derivative is 0. So the curvature for this function is 0 if and only if f double prime of t is equal to 0, and that is the case when f of t is at plus b, or a straight line. So 0 curvature for a function corresponds to the function being a straight line. Any other function will have positive curvature somewhere. Thank you very much.